Voltage drop describes how the supplied energy of a voltage source is reduced as electric current moves through the passive elements of an electrical circuit. Voltage drops across internal resistances of the source, across conductors, across contacts, and across connectors are undesired. Supplied energy is lost. Voltage drops across loads and across other active circuit elements are desired. Supplied energy performs useful work. For example, an electric space heater may have a resistance of 10 ohms, and the wires which supply it may have a resistance of 0.2 ohms, about 2% of the total circuit resistance. This means that approximately 2% of the supplied voltage is lost in the wire itself. Excessive voltage drop may result in unsatisfactory operation of, and damage to, electrical and electronic equipment. National and local electrical codes may set guidelines for the maximum voltage drop allowed in electrical wiring. To ensure efficiency of distribution and proper operation of electrical equipment, the maximum permitted voltage drop varies from one country to another. In electronic design and power transmission, various techniques are employed to compensate for the effect of voltage drop on long circuits or where voltage levels must be accurately maintained. The simplest way to reduce voltage drop is to increase the diameter of the conductor between the source and the load, which lowers the overall resistance. In power distribution systems, a given amount of power can be transmitted with less voltage drop if a higher voltage is used. More sophisticated techniques use active elements to compensate for the undesired voltage drop. Voltage drop in direct current circuits. Resistance. Consider a direct current circuit with a 9-volt DC source, 3 resistors of 67 ohms, 100 ohms, and 470 ohms, and a light bulb, all connected in series. The DC source, the conductors, the resistors, and the light bulb all have resistance, all use and dissipate supplied energy to some degree. Their physical characteristics determine how much energy. For example, the DC resistance of a conductor depends upon the conductor's length, cross-sectional area, type of material, and temperature. If the voltage between the DC source and the first resistor is measured, the voltage potential at the first resistor will be slightly less than 9 volts. The current passes through the conductor from the DC source to the first resistor. As this occurs, some of the supplied energy is lost. Due to the resistance of the conductor, voltage drop exists in both the supply and return wires of a circuit. If the voltage across each resistor is measured, the measurement will be a significant number that represents the energy used by the resistor. The larger the resistor, the more energy used by that resistor, and the bigger the voltage drop across that resistor. Ohm's law can be used to verify voltage drop. In a DC circuit, voltage equals current multiplied by resistance. Also, Kirchhoff's circuit laws state that in any DC circuit, the sum of the voltage drops across each component of the circuit is equal to the supply voltage. Voltage drop in alternating current circuits. Impedance. In alternating current circuits, opposition to current flow does occur because of resistance. Alternating current circuits also present a second kind of opposition to current flow, reactance. This total opposition is called impedance. The impedance in an alternating current circuit depends on the spacing and dimensions of the elements and conductors, the frequency of the alternating current, and the magnetic permeability of the elements, the conductors, and their surroundings. The voltage drop in an AC circuit is the product of the current and the impedance of the circuit. Electrical impedance, like resistance, is expressed in ohms. Electrical impedance is the vector sum of electrical resistance, capacitive reactance, and inductive reactance. It is expressed by the formula, analogous to Ohm's law for direct current circuits.